Okay, so today's notes are all on buffers, and there is a worksheet that you're going to need to pick up. It's due the first class next week. Um, so, good luck on your AP. That's all I can say. So the first thing we have to do is figure out what the heck a buffer solution is. All right. Um, if you read through 16.3, which you don't really have to, but that's all about one of the things in there is buffers. Buffers are a solution that's made up that will resist change in pH when you add small amounts of acid or base. Okay? A solution that resists change in pH when small amounts of acid or base are added. By the way, our blood is buffered, very tightly buffered, at pH 7.4. All of you probably have a pH of your blood between 7.38 and 7.42. And it does not change if you, I don't know, suck on 2 lemons or something, or do something a little crazy. Your body is really good at resisting pH change. About the only time the pH of your blood changes if you're really sick. Like for instance, you're a diabetic going into a coma. They can make so much acid if they're having a crisis that they can actually lower the pH of their blood significantly. If it goes much below 7.2 or 7.1, they're probably dead. So it's good that our bodies are really, really good at buffering the blood. So I'll give you a minute to copy down. Okay, so you're going to see the definition again. These are vocabulary terms, so don't forget them. Usually I try to highlight vocabulary terms in red. So a buffer is a solution that resists change in pH when small amounts of acid or base are added. It's the answer to the warm-up. So if you get a question like that, you got your warm-ups, hey, you'll know the answer. Now, yes?
Learned this yet.
You haven't learned this yet.
Is it going to be graded on the titration worksheet?
Don't worry about it. Don't worry about it. All right. So buffers are typically an equimolar solution of a weak acid and its conjugate base. And so an example would be if we had like 0.05 moles of acetic acid mixed with 0.05 moles of sodium acetate. If you put them in a liter, that would be a 0.05 molar solution of each. So acetic acid is a weak acid, sodium acetate is its conjugate base. Okay? And I'm going to demonstrate that. I have a video that you can watch that shows what happens when you add different amounts of acid and base. So remember, typically an equimolar solution of a weak acid and conjugate base. And as per all things in chemistry, there are other things that can be buffers. You'll learn about them in more advanced chemistry, but this is a good starting point. Now, how do they work? Let's look at the acetic acid sodium acetate system. Okay, so this is acetic acid, this is sodium acetate, it's the acetate ion. I'm just leaving the sodium out because the sodium has nothing to do with a buffer system. It is floating around in the solution, it's just a spectator ion. Now, suppose we add a small amount of base. So we're adding hydroxide ions. What will happen is the hydroxide will react with the hydrogen of the weak acid, and it will make water, and it will make sodium acetate. Now, has the concentration of hydrogen ions changed? Not significantly. All the hydroxide did, it didn't remove hydrogen ions from anything except the weak acid. So the amount of hydrogen ions in solution is the same. So OH doesn't build up, it doesn't become a more basic solution, okay? The OH just gets converted to water and the pH stays the same. Now you have to realize that you can't add an infinite amount of sodium hydroxide. Again, this is referring to what happens when you add small amounts. So sodium hydroxide, the hydroxide part gets converted to water, and you get more conjugate base. Now, what happens if you add acid? Okay, so here's our system. When we add acid, basically the only thing that matters are the hydrogen ions. So we add a small amount of acid. That acid is going to react with the conjugate base. Here's your acid as a hydronium ion, and it's going to make more weak acid and water again. So again, the concentration of the hydrogen ions isn't going to really change. So it doesn't build up, it gets converted to water, and the pH stays the same. I can't stress enough that it's only small amounts of acid or base. You can't put in an infinite amount and expect the pH to stay the same. And I'll demonstrate that when I show you the video. Okay, again, only works with small amounts. Okay, yes, Will?
Since you're making water, does it dilute the solution at all?
It's not going to change the volume significantly. Okay, so one of the buffer systems I wanted to mention, in addition to the acetic acids, sodium acetate one, is citric acid and sodium citrate. So here's what it looks like. Citric acid has 3 acid groups. These are COH2 groups. Remember what citric acid is from? Remember the citric acid cycle in, bio? It's part of the Krebs cycle. Okay. If you react it with some sodium hydroxide, you end up with water, and you have this, which is sodium citrate. So if you have a mixture of citric acid and sodium citrate, remember, you need equal molar amounts to have the best buffer. You want to have the same amount of each present in the solution. And so what will happen is the exact same thing as I mentioned with the acetic acid sodium acetate one. If you add some base, to this, some OH, or if you add, it'll react with the citric acid, making more sodium citrate, essentially, more citrate ion. And if you add some acid, it'll react with the citrate and make more citric acid. Again, as long as you don't put too much in, you'll end up with a very small pH change. Okay. Again, so a 50-50 mix of citric acid and sodium citrate is also a buffer. The reason why I mentioned this one is because I'm going to give you 2 demos. One of the demos is with the Alka-Seltzer. Read the ingredients on Alka-Seltzer. Guess what it's got in it? Citric acid and sodium citrate. Those of you who have tried Kaffee, any of you tried Kaffee yet? It's one of the entrepreneurship capstone projects they're trying to sell at the Shark Tank. I helped them make that. Want to guess what's in it? It's got citric acid and it's got stuff that's going to foam up, all right? That's going to make bubbles, and it's just kind of fun. So it's kind of the same thing. Yes? Next week, Thursday, should be Shark Tank. Okay. Now, I'm going to just show you the data here real quickly so you have it, but I'm going to play the videos now. So what I did first is I took some Alka-Seltzer, dissolved it in water, and I also took some water. So Alka-Seltzer is AS, and I put some universal indicator in it, and it's yellow. Water with universal indicator was kind of yellow-orange. You'll see this in the video. I added some base. The Alka-Seltzer stuff stays yellow. I add some base to water, it turns purple. I add some acid, the Alka-Seltzer stays yellow, and then I add some acid to the water and it turns red. You'll see that in a minute, but this way you can at least see the data. And then we also tested in the video the acetic acid sodium citrate buffer system. So the water here, the starting pH was about 5.9. If you add 3 drops of HCl, it drops to 2.9. Then I put some base in, 6 drops of 1 molar sodium hydroxide went up to 11.2. So you can see it does not buffer the solution, the pH changes. Here is the starting pH of the acetic acid sodium acetate buffer system. It's 4.6. And then I add the same amount of acid as I did to the water, or the same amount of base as I did to the water, and the pH doesn't change at all. However, if I go crazy, I think what I ended up adding was 20 drops of that, and I think I then added 30 drops. So it's sort of out of order. This was added first. So cut, paste. So what I did is I dropped raised the pH with the base first to 11.8, and then I added enough acid to overpower it. So you can see that you can't put an infinite amount of sodium hydroxide or hydrochloric acid into something, or any other strong acid or strong base, because it can only resist a pH change for a while. Okay, so that's it for the notes, and then there's 2 videos.